Okay, so I guess we're going back to a discussion session with the modelers. And some of these topics they've already addressed. So the first, is there anything intrinsic to the method that would preclude it using simulating small magnitudes? And we've addressed that. We've addressed the model resolution limit. We've addressed that. Surface and buried ruptures. You've addressed all of these questions already.
Kind of rushed you at the end, right, of the last section. So were there any other comments? I know, Paul, you had raised your hand earlier. Nothing? Any other comments or questions from the general modeling that we're talking about here? No, that means I have to give you another quiz if you don't ask some questions.
I have a comment.
Okay.
In order to avoid it.
Okay, Christine Goulet, Pierre Berkeley. Quick comment, I saw that you decided to use 32 realizations systematically, but there's one thing that could be done, that's something that I want to implement on the platform, it's not there yet, but you could look at the validation results and write a simple code. I actually have a code I can give you to do that, to see how many realizations you need to capture the mean. And for XSIM, it was like 10, you're sure you got it. You know, and XSIM, of course, runs fast. It's not that big of a deal, but time series are long. So that kind of stuff, I think, would save you a lot of time. Grades and Pitarka takes more, and yours, I don't remember, but I think that's something you should consider, given all the time it takes to do that. Comment over.
What was the largest number you found was needed, though?
We didn't do it systematically for all of them, but so that's something you guys would have to do externally for now. I'll give you the code. It would be much higher for the other methods. Then XSIM is the one that converges the fastest.
Much higher than 32?
No, much higher than 10.
Okay.
But I mean, you could save some time given that, you know, what you're trying to achieve here and how long it takes, because I know these guys suffered the last 3 weeks.
So Gabe and then Tom.
Yeah, that comment by Christine implies a much greater sigma for some models, which is okay. And as Norm said, yeah, you were trying to validate for the mean, but it's something to keep in mind that there are some issues there that in the parameters that
XM sim gives very small variability.
Yeah.
And
Okay.
so that's not, it's
Okay, so it's a weakness on XM sim as opposed to a weakness on the others, you think.
none of the models have been calibrated
For sigma,
variability,
yeah,
right?
no, you said that. I know you said that, but it's something so I guess they didn't calibrate themselves by happenstance.
But if you think about, right, but if you think about normal ground motion models and I gave you 10 and I said how stable is your median, then you would say there's still a large variability.
Right. Okay.
Tom?
One of the enduring problems in making synthetics at short periods has been to try to get the lack of radiation pattern that we see in high frequencies, especially in accelerations for, say, a magnitude 6 earthquake, correct. So when we go to long periods, we see clearly directivity, we see radiation pattern. But when we move ourselves up, say, 3 hertz to 10 hertz, it magically disappears. But when you look at those same frequencies with a magnitude 3, you'll see the directivity, you'll see the radiation pattern, and somehow to put the physics in it that radiation pattern somehow seems to go away when you go from a 3 up to a 6 in the frequency band, say 10 hertz, seems to be an important part of the problem. And I think San Diego State has a way to do that with all the scattering. It's related to but if it's really correct, you'd want it to predict coda correctly in seismograms, and it's a curious question for San Diego whether they've looked at trying to see if they can simulate coda correctly.
That's part of then, can these things go down to magnitude 5.5? how is the radiation pattern coming back into its loop, right?
Yeah,
At what time does it turn on? So I don't, do you have, where is Kim? Can you talk about how you're dealing with radiation pattern, and if we were going to smaller magnitudes?
The radiation pattern is pretty much entirely contained in the long periods up to 1 hertz. Above 1 hertz, the radiation pattern becomes pretty isotropic for the 3 components. So it disappears magically.
Scattering, right?
Yes, 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 exactly.
But part of the time, if you went all the way down to magnitude 3, then you probably have to push that radiation pattern to be showing up at higher frequencies.
Probably.
And is there, at 5.5, is it still completely washed out, or is it sort of, only halfway washed out? I don't know
Right.
the answer.
That's a good question. We should. We haven't actually simulated less than about magnitude 6 until this exercise, so it's kind of a hack to see how it does, and this is one thing to look into. If it does appear that observations have radiation pattern up to higher frequencies, this is something we could incorporate by increasing the merging frequency up to 2 hertz or so. So that's a good point. I'll see what data suggests.
Just to clarify a little bit more, we see the radiation pattern in the main S wave arrival, even all the way down to 3. But when you look in the coda of things, you don't see radiation pattern, presumably because it's scattered from all directions. And the frequency at which you're picking up this scattered from all directions just depends on the size of the source that you're looking at. So.
Any other questions, comments? So for those of you on the GMPEs, think about when we're going to ask you how do we deal with magnitude 5.5 to 6s for hanging wall effects. So that's going to be part of what you have to, I think we're going to talk about tomorrow as we go forward. Anything else, Doug, that you wanted to cover?
Just give the modelers an opportunity to, I guess, discuss the broader results in which there are these plateaus that extend out onto the footwall, and the divots that occur either close to the surface projection of the fault, possibly extending out onto the footwall, that appear to be having some sort of systematic behavior with respect to Z-Tor and also the dip of the fault. If there's any, you had a chance to think about that, and if there's any additional insights as to what might be controlling these observations.
So some of these correlations I think is related to the radiation pattern for the long period contributions. Maybe not entirely, but the shallow events with the steeper dips have peaks close to the top of the fault, which is what we expect from the radiation pattern. For the deeper events, for the shallower dipping events, we see this peak propagating, if you will, further into the footwall side, which is also what I would expect from directivity effects on the up-dip reverse fault. I'm not sure if that explains all of Jennifer's divots and puppets and whatever she's seeing, but the general trend, I think, is in agreement with the broader picture I would expect from the radiation pattern of an up-dip propagating train of waves for a thrust fault with different dip and different depth to the top. So there's some variation that smaller scale variation that I'm like the dips between that extends only one station interval that is probably too fine of a detail to be explained by such radiation pattern. And since it occurs in the long period for both GNP and SDSU, it's obviously not a scattering effect. So I think we have to think more about those features.
I think what might be interesting is to look at those features also in terms of the velocity model, because those waves, the strength of the waves is controlled by the radiation pattern that has directionality, and then how the wave field is refracting through the shallow structure will differ from 1D model to 1D model. And so precisely where the peaks and lows occur with respect to a surface projection of the fault might have some dependency on velocity model. Might be worth it. Rob, are you still on?
Yeah, I'm here. Sorry. It was multitasking.
So the question that we were just discussing is whether you've had a chance to think about the relatively wide areas of higher motions extending into the foot wall, and the spatial relationships between what's being termed a divot with respect to the surface projection of the fault, and how there appears to be a systematic dependency with Z-Tor and the dip of the fault.
Yeah, so I think it is a combination of the radiation pattern effect. So this would be at the longer period following
That's
the
right.
discussion that we just had. But at the longer periods, I think it is more systematic and related to the radiation pattern effect. I think, again, as you get further away on the footwall side, the motions are relatively amplified or larger ground motions. I think that's a combination of ruptured directivity up into the shallow layers and then building up surface waves. I haven't had a chance to look at the waveforms yet to confirm that, but that would be my suspicion. Maybe speculating a little bit further, I think this effect is being modeled correctly given the way that we're representing the fault and the rupture. But I would speculate maybe that model isn't entirely appropriate for the real Earth, meaning that, say an actual fault may have roughness in the surface and the geometry that would tend to break up the coherence of that radiation pattern, even at periods of a couple seconds to a few seconds. And so, my sense is that with the way we're modeling these faults as simple, completely flat planes, and using the 1D velocity models, that may tend to accentuate the coherency and the strength of these effects, even at the longer period.
Yeah, that's a very good point. These are very simple planar fault models, and constructive interference would be maximized. Are there any other questions, I guess, for either Rob or Kim? with respect to these issues with small magnitude events and dipping faults and hanging wall effects. Or more generally, any comments on the comparisons that Jennifer made between the simulation results and the GMPEs.
Thank you. So let's, we're going to have something different now.